Asteroid impacts have always been a fascinating concept. Although uncommon, even today we see news articles of asteroids reaching the surface of Earth, and they make for interesting subjects of disaster movies. Why? Well, they are likely to have caused the mass extinction, which wiped out 76% of all species on the planet 66 million years ago. Was this a one-off? Or could such an event happen again? And if a large asteroid was on course to strike Earth, could we prevent it and survive using current technology? Welcome to this journey with me today as we explore the DART mission, humanity's first attempt to change the course of an asteroid, aiming to protect Earth from future world-ending threats. Major impact events have significantly shaped Earth's history. Going back to the very early solar system, one of the biggest impacts in our history may have formed the Moon, when a planet-sized object named Theia collided with the young Earth. Over time, we might now have oceans full of water thanks to collisions with asteroids. And since then, asteroids have also potentially caused several mass extinctions. One of the most well-known impact events left the Chicxulub crater, which is believed to have caused the extinction of the dinosaurs 66 million years ago. There is an inverse relationship between the size of an object and the frequency of such events. Small objects frequently collide with Earth, while large object collision events are very rare. And as the solar system ages, large asteroid impacts become less common. You see, when asteroids collide with something, they either fragment into smaller chunks, or they get integrated into the larger bodies like the planets. It is estimated that Earth gains 15,000 tons per year this way from meteors entering its atmosphere. Impacts actually happen all the time on Earth. A lot more than you may think, but most are barely noticeable. Meteors, or shooting stars, are tiny objects with sizes ranging from sand grains to stones only a few centimeters across. These burn up as they enter Earth's atmosphere. So, how many do you think hit Earth's atmosphere on a daily basis? The figure may surprise you. 25 million. And guess what the biggest meteor is likely to be on any given day? 40 centimeters across. The biggest one on a yearly basis is around 4 meters, and every century we get one that is at least 20 meters across. The objects that manage to survive the Earth's atmosphere and land on the surface are called meteorites. These have to be somewhat larger than normal shooting stars to survive, and most of the time, what's left of the object upon reaching Earth's surface is about the size of a brick. These objects cause large trails in the sky with spectacular colors, known as fireballs. Every 2,000 years or so, a meteor about 100 meters across hits Earth, blasting through the atmosphere, causing significant damage to the area from the impact itself, but also from the airburst associated with it. And then you have objects large enough to threaten civilizations on Earth, objects over 10 kilometers, that only come around once every several million years or so. The chances of anyone alive today encountering such an event are very close to zero. One of the good things about larger objects is that they are also easier to spot, and scientists think they know of all nearby asteroids above the size of 10 kilometers with a very high degree of certainty. But smaller, less easy to spot meteors are still a big threat on a more local scale. About 1,500 people were injured in 2013 when the Chelyabinsk meteor exploded over Chelyabinsk in Russia. Around 7,200 buildings across 6 cities were damaged by the explosion's shock wave. Luckily, no one was fatally injured during this incident. But imagine if such a disaster were to happen in a highly populated region. Needless to say, the results would be catastrophic, This is why it is very important for us to be able to detect and prevent this before it has a chance of happening. One of the ways to do that is for us to find and track objects in space that might be a threat. And we are doing this faster and more efficiently than ever before. We've discovered over 20,000 new potentially dangerous asteroids in just the past 2 decades, with about 30 new discoveries added each week. Most of them have harmless orbits. But what would we do if ever we found an asteroid that was on a collision course with Earth? This was what NASA was trying to find a solution for with its DART mission, or the Double Asteroid Redirection Test. DART was a joint project between NASA and Johns Hopkins Applied Physics Laboratory, with international partners in Italy, Japan, and the European Space Agency. Its goal? To try to redirect an asteroid's path by colliding a spacecraft with it. Before DART came along, many different ideas were floated about the best way to prevent an asteroid collision. If we had enough warning, and if the asteroid were small enough, we could send a spacecraft to ride along with an asteroid to act as a gravity tractor. Over time, the presence of the spacecraft could gravitationally influence the asteroid just enough to redirect its orbit slightly out of the path of Earth. It sounds a little far-fetched, but in 2015, NASA published an article on their webpage stating that this was a workable solution. Perhaps a more well-known idea is that of just sending in a nuke. Asteroids aren't very densely packed, so exploding them into tiny pieces ought to be easy enough to do. But although this idea was popularized by films like Armageddon, it might not actually work as well in practice, as the momentum of the asteroid would be largely maintained, even as its form shattered into pieces. If you enjoyed this topic, don't forget to like and subscribe to support the channel. If the resultant pieces were big enough, this would have the unfortunate effect of turning a metaphorical bullet heading towards Earth into an equally deadly shotgun spray. A third idea was about sending reflective mirrors to an asteroid. It's a well-documented fact that as comets pass by the sun and heat up, they frequently start out gassing, giving them added propulsion away from the sun. Spacecrafts with mirrors that traveled to an asteroid and reflected sunlight onto its surface at the right location could attempt to cause similar outgassing, letting the asteroid itself propel itself out of the path of Earth with its own released gases. But the creators of DART settled on perhaps the simplest solution, and one that we had successfully pulled off before with a comet, to directly impact the asteroid. Not to blow it up, but to hit it just hard enough to knock it off course. The kinetic plan was settled on, but mission planners needed to greenlight a suitable test asteroid to hit, and so scientists settled on Dimorphos. This asteroid was first discovered fairly recently in 2003. It is the small moon in a binary system, orbiting around the larger Didymos, which was spotted in 1996 by the Spacewatch project in Arizona. Dimorphos is only 160 meters across, which is much smaller than the 780 meters Didymos, and has an orbital period of 11.9 hours and maintains a distance of about 1 kilometer from its larger neighbor. The system orbits the Sun every 2.1 Earth years and made its approach to Earth in October 2022, coming within 10.6 million kilometers, the closest it's been since 2003, meaning this was the perfect time to visit it. It was this closeness that caused NASA to choose Dimorphos as their target. It was relatively easy to get to, but crucially, it was not so close as to be on a collision course with Earth. Scientists were confident that even once knocked off course, the Earth itself would not be in any danger. With their target set, NASA needed to build the perfect spacecraft to perform the deflection. Compared to other spacecraft, DART doesn't have a lot of frills. It's about the size of a refrigerator and weighs just 610 kilograms, which is minuscule compared to Dimorphos's estimated weight of 5 billion kilograms. DART has one payload, an aperture camera called Draco, short for Didymos Reconnaissance and Asteroid Camera for optical navigation, as well as sensors and an autonomous navigation system. It also comes paired with a small secondary spacecraft called LICIACube, making it a binary spacecraft visiting a binary system. Built by the Italian Space Agency, ASI LICIACube is a small CubeSat with its own autonomous navigation system designed to separate from DART 15 days before impact. LICIACube is tasked with recording the impact and its aftermath, with two optical cameras named Luke and Leia. Yes, you heard that correctly, Star Wars fans. The LICIACube weighs just 14 kilograms and is only about 30 centimeters long. It would fly by the asteroid system using its own autonomous navigation system. The DART spacecraft was also designed to be running autonomously. Due to the latency between sending and receiving instructions caused by the distances between Earth and the spacecraft, DART needed to locate the moonlet, detect a perfect spot for the impact to happen, and then aim itself appropriately. This is where DART's Smart Nav came in handy. This autonomous optical navigation system could identify and distinguish between the two bodies and detect the target, and then direct the spacecraft toward it. And surprisingly, all this would happen within only an hour before the impact. After blasting off on November 23, 2021, on a SpaceX Falcon 9 rocket, DART spent the next 10 months in transit. In the 4 hours leading up to impact, at a distance of 90,000 kilometers, DART's internal navigation system took over, and 90 minutes before impact, its Smart Nav system put the spacecraft on its final trajectory. When DART was 24,000 kilometers away, Dimorphos became visible on camera, taking up 1.4 pixels. This is one of Draco's last images where you can see both Dimorphos and its parent Asteroid in the same frame. As DART hurtled closer to its target at a speed of 22,000 kilometers per hour, Dimorphos and its potential impact site came into spectacular view. In this image, taken just 3 seconds before impact, you can really see how Dimorphos is a loose pile of rubble, essentially leftover from the solar system's birth. This remarkable photograph is DART's final fully transmitted image. It was taken at a distance of 12 kilometers, a mere 2 seconds before impact. For reference, the scale is roughly 3 centimeters per pixel. And here, finally, is DART's last, partially transmitted image. The downlink was interrupted by DART's previously scheduled, shall we say, disassembly. As strange as it sounds, this is my favorite of these images. Its incompleteness seems to capture the drama and intensity of the moment, as though freezing for all time the breathtaking instant when DART completed its 17.5 million kilometer journey in the blink of an eye. To the very end, DART did what it was designed to do with incredible precision, and it's a testament to the ingenuity of those of NASA. Here is the entire sequence, sped up and played as a time-lapse. The video you see corresponds to the final 5.5 minutes of DART's final trajectory. As you'll notice, some of the images look a bit blurred. That's because DART's ion thrusters came into play, causing vibrations to the spacecraft and its camera. This sequence is incredible to me due to the speed involved. It hit such a tiny object. And I'm astonished some of these images are in focus at all. Imagine how quickly the camera had to adjust to the rapidly approaching object. Now, I'm sure you're itching to know whether the impact was successful. To relieve you of the suspense, the answer is yes. In fact, the early results have surpassed expectations. Before DART's kinetic impact, NASA defined success as a change in Dimorphos's orbital period of at least 73 seconds. Yet based on what we know so far, the data shows that DART shortened Dimorphos's orbit by a full 32 minutes, from 11 hours and 55 minutes to 11 hours and 23 minutes. Even with a margin of error of plus or minus 2 minutes, That is 25 times NASA's benchmark. A truly remarkable outcome. The impact released 19 gigajoules of energy, the equivalent of nearly 5 tons of TNT, and blasted a crater up to 150 meters wide in the asteroid's surface. Pretty big, considering the moon was only 160 meters to begin with. Share this video and hit the subscribe button to keep exploring the universe together. It was also enough to change the shape of Dimorphos's orbit and the asteroid itself. Dimorphos's orbit was originally very circular around Didymos, but after DART hit, this path became more elongated. The orbital time also continued to drift over the next few weeks, before settling on 11 hours, 22 minutes, and 3 seconds. As for the shape, before the impact, Dimorphos had what is known as an oblate spheroid shape, a bit like a slightly squashed ball. Afterwards, it had become a triaxial ellipsoid, similar to an oblong watermelon. It's fascinating to consider the forces that must have been at play for this change of shape to occur. It also highlights the fluffy nature of asteroids like Dimorphos. Being so loosely tied together by gravity, it increases the capacity for shape changes like these to happen, if hit with the right impact. Not to worry though. Even with large margins of variability, scientists know that even with this collision, the orbit of Didymos won't change enough to ever cross paths with Earth. But if there was an Earth-bound asteroid, this little nudge early enough in advance can impact its orbit enough to take it off a collision course. But why did the impact shorten Dimorphos' orbit? Well, due to orbital mechanics, the crash pushed Dimorphos closer to Didymos, which in turn sped up its orbit. Scientists confirmed this finding through observations from optical telescopes here on Earth, including the Southern Astrophysical Research Telescope in Chile. SOAR also happened to capture some of the very best images of the encounter, including this breathtaking photograph of a 10,000-kilometer trail of debris 2 days after impact, making it look like a comet. Because Didymos is a 2-asteroid system, its brightness fluctuates as Dimorphos passes through the shadow of its parent asteroid and out again in front. By tracking the light curve, scientists can calculate the speed of Dimorphos' orbit. These results were further supported by radar data collected by observatories in California and West Virginia. DART and Earthbound telescopes weren't the only cameras watching the event, though. The closest images of the crash scene were captured by LICIACube, and they are phenomenal. As I previously mentioned, LICIACube separated from DART 2 weeks before impact to conduct its own flyby using its autonomous navigation systems. 2 minutes and 45 seconds after DART's impact, LICIACube flew past Dimorphos to photograph the impact site with its evolving plumes and ejecta. Here is an action-packed image of Dimorphos after the impact, with Didymos overexposed in the foreground. Notice the huge plumes of material emanating from Dimorphos. Some of them seem to be spiraling, almost like tendrils of a vine. This indicates that the material changed directions as the plume grew. We think this phenomenon may be caused by the composition of the asteroid, as impact tests on finer sediment mixed with coarser debris sometimes yield similar ejection patterns. This is a more distant image, also captured by LICIACube, with Dimorphos on the rightmost side. Notice how the asteroid itself is barely visible due to the huge clouds of material splashed up by the impact. Hubble and the Webb telescope also got in on the action of imaging the aftermath of DART's impact. Here, you can see a spectacular series of images from Hubble showing the progression of the plumes in size and number. Notice how some of the plumes look like rays emanating from the asteroid. Strangely, some of these rays appear curved. Why? As of now, NASA isn't sure. While Hubble has observed the impact from the visible spectrum of light, the Webb telescope captured its own images from the infrared spectrum. This is pretty impressive, since Dimorphos was traveling 3 times faster than Webb was meant to be able to track. The time-lapse you are looking at starts right before impact and continues until 5 hours afterwards. Notice the sudden flare of light, coinciding with the material released from impact. I also love how the Webb images give you a great sense of the spiraling plumes emanating from the asteroid. Over the coming weeks and months, scientists will continue to study the data from DART's impact. But the real investigative work will be carried out in the future by Hera. Hera is a follow-up mission currently being carried out by the European Space Agency that launched on the 7th of October 2024 and will reach the Dimorphos system by 2026. Carrying a sophisticated payload of instruments including cameras, a spectrometer, and an altimeter. Once it arrives, Hera will intricately document the size, shape, and composition of the crater left behind by DART's impact. Most exciting of all, Hera will conduct observations of Dimorphos's internal and subsurface structures. This modeling will not only advance our understanding of the binary Dimorphos system itself, but provide a more nuanced understanding of how a NEO's physical characteristics influence the transfer of momentum, as well as how kinetic energy transfers to a NEO and its ejected materials. All of this will allow for a greater understanding of DART's kinetic impact and provide a useful guideline for improving deflection technologies in the future. So, combine that with NASA's missions like NEO Surveyor, which aims to discover at least 90% of asteroids 140 meters in size or larger, and it feels like humanity for the first time has actively reduced its chances of being hit by the kind of world-ending impact that likely wiped out the dinosaurs. NASA already keeps track of most NEOs, but some asteroids like dark comets are harder to see as they don't reflect much visible light. NEO Surveyor is proposed to launch in 2028 and will scan the solar system for such objects by taking infrared readings, detecting hard-to-spot asteroids by seeing the heat they radiate when they are warmed by the sun. It also will be able to spot asteroids that approach Earth from our blind spots, such as ones coming directly from the direction of the sun, which ground-based telescopes might miss due to the glare. With even the hardest-to-see NEOs being detected, the technology proven by DART will be a shield that can keep our world safe. So, there we have it. Everything you could want to know about the DART mission. Right now, we've barely scratched the surface of deflection technologies. But if you look at what this mission has accomplished, it appears the future of planetary defense has taken a bold and promising first step. Thank you for joining me on this incredible journey through the DART mission, a pivotal milestone for the future of planetary defense. Right now, our technology may only be scratching the surface of what's possible to protect our planet, but every small step we take is writing a new chapter, bringing hope and confidence to humanity as we face the vast threats of space. If you found this video helpful or have any thoughts to share, don't hesitate to leave a comment below. I always look forward to hearing your opinions and stories. Please hit the like button, subscribe, and turn on notifications so you won't miss any upcoming journeys, scientific knowledge, or fascinating stories about the universe. Your support is truly the motivation for me to keep creating even better content. Thank you so much for being here, and see you in the next video. Goodbye and have a wonderful day, everyone.